So what I want to do is start out by answering those questions. If you have questions to add to the mix, let's do them, okay? Just as a reminder, we finished up section 1.3 on Monday. So you now have had homework assigned through 1.3. I will be sending an email out to the class tomorrow, as usual, reminding you of upcoming due dates and that sort of thing, just so that we're all on the same page with stuff. And also reminding you that a week from today, we're Zooming class, not doing it live. Cool? All right, so the two questions that were asked are as follows. I'm going to do the one from 1.2 first, just because I kind of like going in order. Imagine that. Okay. And I know we've gone through some of these, but I think it's important that we really make sure everybody has a clear understanding, because I think that people's questions tend to fall very much in the same place, and things can look and get pretty funky. Okay. So the first one is for us to graph a piecewise defined function, because we just can't get enough. Yeah. So the one that was asked for me to do looks like this. Yeah, sorry. Yeah, and I can adjust the light as well. Thank you for asking. Okay, so if we want to graph this, we want to go in pieces, okay? What I want to remind you of is this deals with where on your Cartesian coordinate system you're actually plugging in the values. Okay, so the functions defined in pieces, one of them is from -2, smaller. One of them is between -2 and 1. And then the third one is for values greater than 1. Okay. So I'm going to start with my two constant functions. Okay. Notice when x is less than or equal to -2, what is my y value or my function value always? -1. Okay. Notice that this is our constant function, our horizontal line at -1. And that starts from -2 and it stays constant from there on over. You with me there? The next part I'm going to do is my other constant function, just because I like getting those out of the way. Now, we also see that my function value is -1 for values of x greater than 1. Okay, whenever you have a strict inequality, in other words, no equal to, you put an open circle there, and then it's -1 in that direction. Are there questions here? And Megan and Finn, if you have questions, please feel free to unmute and ask. I'm super duper happy to answer. All right, so the issue is what happens between -2 and 1, okay? We see here that we're going to have an open circle, and here we're going to have a closed circle, because right here we have a strict inequality, and here we actually have the equal to sign. Well, how is this middle function defined? Isn't this my identity function? In other words, whatever x is, so is my function value or my y value. Okay, another way we think of this is y equals x. So for example, I'm going to have an open circle wherever my function value at -2 is. If I plug -2 in here, won't -2 come out? Notice I have an open circle there because that's kind of a starting point. okay? We can take other points. If I plug in x equals -1, what's going to come out? -1, 0, 0. And then if I go all the way to 1, 1 is going to come out. Notice I have a closed circle because I'm actually interested in that function value. Is that okay? So again, notice it's a constant function of -1 when x is less than or equal to -2. It's a constant function of -1 for values of x greater than 1. And in between these values, notice I have a closed circle when I plotted my x equal 1 value, and I have an open circle when I plotted my -2 value. Diagonal? Okay, let's graph. Do you agree we're looking at the graph of y equals x? Let's just plot some points, okay? Kiki, thanks for asking a question. No, I'm totally serious. So if I plug in x equals 0, what's y going to be? 0. If I plug in x equals 1, what's y going to be? 1. If I plug in -1, what's y? -1, okay? So if I just plot these 3 points, I have 0, 0, 1, 1, -1, -1. It's a diagonal line. Yeah, and we just want that diagonal line in this region here. Hooray for questions. All right. The next one I'm going to do is from section 1.3. This looks a lot different. It's a very different type of question. So suppose f of x. Now you're all going to have homework problems similar to this. It's not going to be exactly this. But maybe it will. But what we want to do is find the average rate of change on the interval from 8 to 8 plus h. You can all answer with an ew right now. It's okay to have those natural emotions. All right. Well, before I do anything, I'm going to first ask myself, well, what does it mean to find the average rate of change on this interval? Okay. And using my formula for my average rate of change, it's the function value at one minus the function value at the other divided by the difference in those values. Y'all with me there? Okay. So from here, I would totally say do side work. We need to know what is f of 8 plus h, and we also need to know what is f of 8, okay? So what does it mean to find f of 8 plus h? It means everywhere where we see an x in our function f, what are we going to plug in? 8 plus h. So isn't that 1 over 8 plus h plus 4? And will you grant me I can write that as 1 over h plus 12, or you could write 12 plus h, doesn't matter. You with me there? It could, but you want to combine numbers when you can. Okay, what if I want to find f of 8? What do I get there? 1 over 8 plus 4. So don't I get 1/12? Finally, a number. You with me this far? Okay, So now let's take these things and plug them in up here. F of 8 plus h is 1 over h plus 12. Minus f of 8 is 1/12. And what happens in my denominator here? My 8's cancel and I'm left with an h. Okay, doesn't look very pretty, but we will make it look really, really pretty. Okay, so what we have now is 1 over h plus 12 minus 1/12 over h. And what we want to do is make this look nicer. Now, there's a bunch of different ways to make this look nicer. You may recall that I called this a complex fraction at one point. What I would suggest you do is you take your denominators. Do you agree your common denominator would be this times this? Okay, so you multiply and divide by it. So I'm going to multiply and divide. Okay, because if we multiply and divide by the same thing, we're not changing any value, right? Because anything divided by itself is simply 1. Notice I put the 12 to the left just because it looks nicer. It doesn't matter which side you have the 12 on. Okay, you can get a common denominator here, but this would be your common denominator anyway. Do you all see how that would be your common denominator? People get confused by that. A lot of times, like if you have 1 over x plus 3 and 1 over 3, a lot of people think x plus 3 would be the common denominator, but that's not the case. It's the product of these two. I mean, think of it this way. 1/5 and 1/3, wouldn't your common denominator be 15? But isn't 1/5 the same as 1 over 2 plus 3? You didn't just take the 3 for the common denominator. So when you're finding the common denominator of these things, you just multiply them. Alex, is that okay? Okay, so I asked myself, what would my common denominator be? Wouldn't it be h plus 12 times 12? That's what I have here. Okay, so here, let me write out each step. Ooh, I think my pen's going blank. So when you're simplifying complex fractions, okay, step 1, determine the common denominator. Do you agree it's 12 times h plus 12? Okay. Now, I think that the niftiest way to simplify this sort of thing, you could find a common denominator in your numerator and do this, but I'm showing you kind of a shortcut method. What you then do is take that value and multiply and divide by it. Okay, so 12h plus 12 times my numerator, 12h plus 12 times my denominator. Now you might ask, why did I do this? It simplifies this very nicely, but notice I'm not changing the value of the original thing I started with, because when you multiply and divide by the same thing, it cancels out and you're essentially left with the same. Okay, now, how do you deal with this from here? Well, leave your denominator alone. What we're going to do though, is we need to distribute in our numerator. Do you agree? So I need to take 12h plus 12 times my first term. And now I need to take this 12 times h plus 12 times my second term. And I'm just going to put my h next to my 12. like that. Do you see what I've done this far? I know my way's better. I did an example like this in class. I can show you the other way too, but let me show you how nice this cleans up, because you're going to be like, ooh boy, that is sweet. Okay. Notice we're multiplying, but I've got a term in my numerator that's the same as in my denominator. What do? They cancel out. What are you left with? 12. Okay, I got my minus. I have a term in my numerator that matches with my denominator. What happens to those guys? They cancel out. Now I have more than one term here, so Kiki, here I would want my parentheses. Now what I'm going to do is distribute the negative sign throughout my parentheses. What's left in my numerator? Negative h. Yeah. And now doesn't this h cancel with that h? So you get negative 1, 12, h plus 12. Did you go and find your common denominator and simplify your numerator that way? Okay, so you did this. Okay, let's do it that way. It's equivalent. Okay, so you did the same thing. You said, oh, my common denominator is 12 times h plus 12. So let's get it in both of these terms. So here we're missing the h plus 12. So we multiply and divide by it. And here we're missing the 12. So we multiply and divide by it. So do you agree this fellow becomes 12 over 12 h plus 12 minus h plus 12, 12 h plus 12 all over h. Okay. Well, let's keep going. Oh boy, we have a common denominator in our numerator, so we can put it over one fraction. I have in my numerator 12 h plus 12 right down here. And then up here, I have 12 minus h plus 12. And then that whole thing is over h. Okay. Well, we still need to get this thing cleaned up, right? So do you agree we would distribute the negative throughout our parentheses? So I'd have negative h over 12 h plus 12 over h. You with me this far? Okay. Well, let me rewrite this another way. Do you agree that this is saying what we have here? We're taking this numerator and we're dividing it by h. Well, when you divide by something, what do? You multiply by the inverse. This h cancels with that h. We still got that pesky negative. You end up in the same place.
So you combine 12 minus h plus 12, and then 2 separate sub of that. So you set 12 times h plus 12. You combine. You didn't combine.
Okay, so what we did is we had two fractions here. Do you agree the only way we can add and subtract fractions is if we get a common denominator? Right, like if I want to take 1/5 plus 1/3, what's my common denominator? 15. So my first goal is to write 1/5 with the denominator of 15. And we multiply and divide by 3 to get there. So do you agree it's 3/15? And similarly, if we want to write 1/3 with a denominator of 15, what do we need to multiply 3 by? 5. But if I multiply my denominator by 5, fair is fair, I need to multiply my numerator by 5. Are you with me on this example? Okay, so let's just have it look a lot worse. Let's do that. What if I have 1 over h plus 12 and 1/12? Well, my common denominator, just like here, I multiplied to get 15. My common denominator would be the product of those two. 12 times h plus 12, okay? So the first thing I need to do is ask myself, how do I write this equivalently with this? Well, from this denominator to that denominator, aren't we multiplying by 12? So I need to multiply my numerator by 12. Okay. Which is what I did right here. And notice I got that. Now what I need to do is write 1/12 with the same common denominator. Well, what am I missing going from here to here? H plus 12. So if I multiply my denominator by h plus 12, I need to multiply my numerator also by h plus 12. And that's how I got this thing up top. Then from here, what I did is I said, well, I've got a common denominator. The whole point of doing that is putting it over one fraction. So I took this 12h plus 12 denominator and I took my numerator, 12 minus this term. What don't you like? Well, because when you subtract two fractions and you already have a common denominator, you leave your denominator alone, right? Yeah. Okay. So like let me take this one step further. If I want to do 1/5 plus 1/3, 1/5 is the same as 3/15. 1/3 is the same as 5/15. When you add two fractions with the common denominator, you leave your denominator alone. You just combine your numerators. Cool. You are so awesome for asking these questions. Like we need to, if there's nothing else that I convey to you in this class is you've got to ask these questions. I appreciate you, seriously. People don't like fractions. I mean, fractions are great to me because I love banana bread. Well, I love to eat and therefore like, well, not that I really pay that much attention to how I cook, but you know, you kind of have to measure certain things, right? Are there other questions on any of the homework? Yeah. On 1.3, okay. So what I'm going to, do you want me to do your version or should I do whatever version comes up for me? Okay, because I'm always happy to do specific versions if that would be helpful for you. Let me go into my open math and I will share my screen. 1.3. Okay. Now I'll share my screen. Cool. So you want to do the last question? This guy. All right. So I'm going to copy it down on this sheet, and then I'm going to turn off this portion so people can see. So this is going to frustrate you for a second. Yeah. Okay. So do you agree, if you want to find the average rate of change between these points, what you need to do is take your function value at one minus your function value at the other, and then subtract off the difference between those points? The thing is, they already gave you the function values, right? Let's compute g of -4. Do you agree that's -4 times -4 squared plus 4? Boy, those are some bounding fours. Well, -4 squared is 16. And 16 times -4 is -64 plus 4. Oh, boy, were they, did I miss a negative? Yes, I missed a negative, no wonder. I need my reading glasses. Gosh, you guys getting old, man. That's you every time. Seriously, I'm like, I know I'm not reading glasses, but I am. Okay, so we get -60. We already have that. Notice we could compute g of 3, but we're going to get -32 out. So literally all we're going to do here is find the slope of the line containing these points. So I'm going to have -32 minus a -60 over 3 minus a -4. Minus a negative is plus a positive. What do we get in our numerator? 28 minus a negative plus a positive. So we get 4. Well, I can look at, if you feel like your answer is correct and you were marked wrong, that's when you want to hit message instructor. But I'll look at yours. I'll make a note in particular to look at yours. Cool. Yeah. If ever you feel like you're working on these things and you think your answer is right and you're being marked wrong, remember, a human programmed this, so mistakes happen. Yeah, I mean, I'll look at your particular version. This is the one that came up for me. Okay, and your last name is Lau, correct? Okay, got it. Other questions? All right, so one thing that I want to emphasize before I continue on is, you know, I give you all a week from when we finish an assignment to do the homework. My strong suggestion is that you do it as soon as you can while it's fresh in your head from us talking about it in class. Again, I'm totally cognizant of the fact that you all have lives outside of school, work, other classes, social, you know, all of that fun stuff. But the more you can keep on the math homework, the better off you're going to be. You know, math is one of those subject areas that you should be practicing at least even a couple problems every day, just to kind of keep yourself in that mindset and in that shape. So if you've already done all the homework and you get it, cool, that's awesome. If you've done the homework and you want to have some extra practice going on, once you're done with your homework, you can always go back into a completed assignment and try similar problems, and it will not change your grade. Okay, I keep every homework assignment open for additional practice after the due date because, you know, in my mind, learning never ends. So. And I totally get it. If you don't really like your home, if you don't like your homework, if you don't like math, I get that it's total pain. I would just say then, you know, maybe rethink going into a STEM field, because STEM fields tend to have a lot of math in them. Yeah. Y'all okay? Are you sick of this dreary smoke? I'm pretty over it, but nobody asked my opinion. Okay. You sure there's no other questions yet? Okay. So what I'm going to do is I'm just barely going to start section 1.4. Okay. I will just make a comment that according to your syllabus, our first test is 2 weeks from today. It might not be. We'll see how it goes, right? Because if you have a lot of questions, for goodness sakes, I want to be able to answer your questions. So I'm just giving you the heads up of that, but you know, that's to be changed if needed, and you'll always have a week advance notice of tests. Okay. So I think this is a really cute section. Can't believe my pen's running out of ink. Let me just go to the blue pen. Composition of functions. Okay. So I don't know what you know about composition of functions. Essentially, when we have two functions, some of the things that you've probably done in your past is you've added two functions, or subtracted two functions, or multiplied or divided. Okay. Another operation that we do with functions is composition of functions. And I think of these as like an assembly line, even though, you know, assembly lines just aren't as common of things anymore. But anyhow, that's how I think of them. Okay. So what I want to say is when you're talking about the composition of functions, what you're saying is you start with some value. Okay. Some value of X. And what you do is you plug it into a function. Do you agree that f of X is your output? Right? Because the output of a function is your function value there. Any questions on this notation so far? Okay. Now, what we like to do then is plug it into another function. So whatever came out of here, I'm going to plug into a function that I'll call G. Okay. What does it mean to plug this yuck into G? Doesn't that mean we're looking at G of that value? So, well, I don't have socks on, but pretend, okay? So like you start with the barefoot. Get out of bed, you got a barefoot. Chilly out. You're gonna put a sock on your foot, right? So I started with a barefoot, now I got a sock foot. Okay, here, we'll pretend that this is a sock. Okay, so I started with a barefoot and now I got a sock foot. All right, now what I'm gonna do is take this sock foot and plug it into my shoe. Okay, so this is my X, that's my foot, okay? My first function was put a sock on it. So I put a sock on it and this is my f of X, it's my socked foot. I take that socked foot, that output, and my next function is put a shoe on it. So then I put a shoe on it, okay? Another way I think of it, again, is with an assembly line. It used to be the case when they would build automobiles, for example, it was done on an assembly line. So you would have one person here and whatever came through, like, oh, this came to me. It's my job to tear off page. And then I pass it to the next person. And then it's their job to crumple it up, right? So whatever comes out of your first function goes into your next function, okay? Now, notation-wise, that looks pretty funky, right? But notice, if I look at this here, I started with my x. I first plugged it in my function f. And then whatever came out, I plugged into my function g. Okay? I could start with some value x and first plug it in g. What comes out of that? G of x. Now I'm going to plug that into a different function. In other words, I'm taking that value g of x and I'm plugging it in my function f. The key thing is work inside out. Okay, you're not multiplying here. What we're saying is composing them. Have you seen this before? Maybe? Okay. So what I want to do now, in my case, I would be kind of, it made more sense to first put a sock on and then a shoe on. It really wouldn't have made sense to put my shoe on and then a sock on. But, you know, sometimes you can do things in either order, right? So what I want to do is just give us an idea of what this looks like. Okay, so I'm just going to make up a couple of functions and we're going to play with this with actual numbers. We're going to get funkier, okay, because we're going to play with it with actual functions too, where we're not just evaluating them at particular numbers. Doesn't this sound fun? It's like a game. Okay, so I don't know. Let's have f of x be 2x plus 3. And let's have g of x be x squared plus 1. You might ask, where did those come from? My brain. Okay, I just made up those two functions. They're the two functions we're going to start playing with. So what if I want us to find, say, g of f of 0? Okay, what I'm going to do is start inside. I'm starting with 0. Who am I plugging it into first? F. So I need to find what is f of 0. Can y'all tell me what f of 0 is here? 2 times 0 plus 3. Oopsie. Which is 3. You agree with that? Are there any questions how we got 3 out? Ask if there are. Okay, so we got that to be 3. So now what we do is we take that output and we plug it into G. In other words, we compute G of 3. I think of this as like hopscotch. Do people still play hopscotch? What do we get out? 10. Are there questions on this procedure? This isn't the only example I'm doing. I mean, for example, I'm going to do f of g of 0 as well. So now, in this case, I would start with 0, but what would be the first function I plug 0 into? G. Can I find g of 0? Here's g of x. We can find g of 0. And that's 0 squared plus 1, which is 1. So what am I going to do with this value of 1? Plug it in for f. Okay, so now I'm going to find f of 1, which is 2 times 1 plus 3, which gives me 5. You with me there? What are your questions? Because I wanted to show you both directions. Yeah. You'll be asked to compute very specific things. Okay, so I did it both ways with my same starting point to show you don't get to the same place, but one would expect that. All of this was just totally made up. Okay, so let's take these same functions, but why don't we do f of g of -2? Okay, where do I start? Good job. I need to find g of -2, don't I? So g of -2, here's how g of x is defined in this particular exercise. So it's -2 squared plus 1. Would you grant me I get 5? Okay. Now check this out. Okay. Do you agree that we found g of -2? What did we find g of -2 to be? 5. So in place of this g of -2, I'm going to write 5. Can I find f of 5? F of 5 is 2 times 5 plus 3. So we get 13. It's my 1 o'clock class's favorite number. Whenever I do examples, I'm like, what's your favorite number? And everyone's 13. Okay, cool. Love how. Okay. Is this okay so far? Ish? Okay. Now, we're going to get bigger than this. I only have 4 minutes, so let's not get bigger today. Or if we're going to get bigger today, let's go home and eat a really good meal by doing that, right? But foreshadow for Friday. What we're then going to do Friday is ask, what if I wanted to know what happens if I plug one function into another in general and going the other way? Ta, 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 ta. See you Friday. Cliffhanger!